Okay, here is our first example. After a special medicine is introduced into a petri dish, a bacterial culture, the number of bacteria remaining in the dish decreases rapidly. The number of bacteria decays by a factor of 1/15 every 6.7 minutes and can be modeled by function n, which depends on the time. Before the medicine introduced, there were 90,000 bacteria in the petri dish. So first, what I need is our initial amount. For this one, I can see before it was introduced to the medicine, there were 90,000 bacteria. So that's my initial amount. Next, I'm looking for my rate. So this one has an exception. You see this word factor? If it says factor in the formula where it says 1 plus or minus, instead of us actually adding or subtracting a rate, we're just going to fill in that whole factor. So our factor will be 1/15. And this is going to happen, our time that we're looking for, every 6.7 minutes. So see that timing's a little bit weird. We're not talking about every minute. We're not talking about every year. There's a specific interval that we have to be aware of and plug into our formula. So now that I have those values, I can plug it into that formula that we talked about. Again, that's A times 1 plus or minus the rate to the T over time. So my A is my initial, so that's 90,000 times. Now, normally, if it's a percentage or a rate, it's 1 plus or minus whatever that rate is. Since we have here a factor, we're going to replace that whole 1 plus or minus R by that 1/15. Remember, factor is the word you're looking for. It's already doing that rate work for you, so you can just plug it in. Then our exponent is T over, that T always stays the same. That's the value that will be replaced. Our weird interval, which is 6.7. And this is your model. You can plug this in, you can solve it for however many bacteria are going to be left over whatever amount of time.